All right. Good morning, everybody. Welcome back. So before we start the lecture today, so let me make a quick announcement here. Okay, so the deadline listed on Canvas for homework 1 part 1 was incorrect. So the correct deadline is September 2nd, okay? And it was already updated on Canvas. For part number 2, I will keep the deadline September 9th, which is next week. Okay, very good. So if you haven't done the homework yet, I would strongly recommend you to don't leave for the last minute, okay? So you're just making hard on yourself when you do that. Okay, so let's go back here a little bit. The last thing we talked about on Monday was regarding the Rutherford atomic model. So this model basically has a small nucleus where most of the mass is concentrated and also the positive charge and electrons around the nucleus, okay? So for the first time, we have two different regions in the atom. So what I want to do today is to talk a little bit more about the atom and the components of the atom. So let's start by drawing a neutral element that has 4 protons using the Rutherford atomic model, okay? So remember that the positive charge is concentrated in the nucleus. So I'm representing here the 4 protons as 4 positive charges. And let's put electrons around the nucleus, okay? And remember that we are talking about a neutral element. So let me switch my screen really quickly here. Okay, so if we are talking about a neutral element, that means the number of positive charges is equal to the number of negative charges. If you have 4 protons, that means you have 4 positive charges. Therefore, you need to balance those 4 positive charges with 4 negative charges. So every time we talk about neutral element, number of protons has to be equals to the number of electrons, okay? In chemistry, we will always play with electrons, okay? Nucleus, they stay as it is. Because we have a lot of positive charge concentrated in the nucleus, there is a lot of repulsion, okay? So therefore, this nucleus is not stable. To stabilize the nucleus, we are going to introduce a new particle to decrease the repulsion. So we are going to have a positive charge separated by a neutral charge. So this way, the repulsion is going to be decreased. And this neutral particle is called neutrons. Okay. So therefore, neutrons are part of the nucleus and they are needed to decrease the repulsion between proton-proton. And now here we have everything in place. In the nucleus, we are going to have protons, which are positive, neutrons, which are neutral, and outside the nucleus, we have electrons which are negatively charged. Okay, so for this course, we are going to focus heavily on these guys here, the electrons. Okay, very good. Let's talk a little bit more about neutrons, protons, and electrons. Okay, for neutron, symbol N10, mass in AMU, atomic mass units, we are going to consider the neutron as a unit, and the charge relative to the electron is 0. For proton, P11, mass is going to be 1 unit as well, and the charge relative to the electron charge is 1 plus. And finally, electron, E0 minus 1, very light particle. So we are going to consider mass 0 and the charge 1 minus. Okay. So therefore, most of the mass of an element is the sum of the number of neutrons and the number of protons, and it is heavily concentrated in the nucleus. Okay, guys, very good. Let's see here how we represent an element. So every element has a symbol. On the top left corner, we are going to represent the mass number. Mass number is defined as the number of protons plus the number of neutrons. So therefore, mass number is always going to be an integer. Okay, careful with that. And on the bottom left corner, we are going to represent the atomic number. Definition of atomic number equal to the number of protons. If the net charge of this element is 0, that means number of protons equals to the number of electrons. Changing the net charge means a change in the number of electrons. Okay, attention with that. We will never change the number of protons. We will always play with the number of electrons. If the net charge is positive, that means we have number of protons higher than the number of electrons, and negative, vice versa. Okay. To calculate the net charge, you can do number of protons minus number of electrons. Okay, very, very simple. Attention here, each element is characterized by an unique atomic number. So therefore, the atomic number will tell us what is the element we are talking about, and it is unique for each element. Okay, so let's do a quick practice here. So I'm going to do the first one with you, and then I will give you a couple minutes to think about the second and third examples here. So if you don't have a periodic table with you, I would strongly recommend you to do that. So you can always use a periodic table, and that's going to help you a lot. Okay, so let's fill up this table with the informations that we need to put here. And I'm giving you here, the only information is for this element, the symbol is Cl. We have on the bottom left corner 17, and on the top left corner 36. So first things first, go to the periodic table. The element Cl is chlorine. So that's the very first information that we can get here. So we are talking about chlorine. The number on the bottom left corner is always the atomic number. And that is unique for each element. And atomic number by definition is equal to the number of protons. So therefore, we can fill up the column here for number of protons. Okay, so right out of the gate, we can get the name of the element and the number of protons. And remember that the number of protons is the number of positive charges. Let's try to figure out the number of neutrons now. So now redirect your attention to the number on the top left corner. Here we have mass number. And by definition, mass number is the number of protons plus the number of neutrons. Let's do a quick math here. We know that the mass number is 36. We know that the number of protons is 17. And is left for us to determine the number of neutrons. Therefore, number of neutrons for this element is going to be 90. And we can also fill up the mass number here, 36. Okay, finally, what's left here? Number of electrons. First thing is to figure out if you are talking about a neutral element or not. The charge for this element is always going to be here on the top right corner. So that's where the charge is going to be located. If there is no number there, that means we have a neutral charge. Therefore, if we have 17 positive charges, to balance those out, we are going to need 17 negative charges, therefore 17 electrons. And that's how, from the information I provided to you, you can figure out name of the element, number of protons, neutrons, electrons, and mass number. Okay. So let's take a couple minutes to think about second and third examples here, and then I will do with you. All right, so let's tackle NE 1020. NE stands for neon. First information that we can get here. Look at the bottom left corner. So here again, we have atomic number. By definition, this is the number of protons. So therefore, we have 10 protons for this element. And it is the number of positive charges. Now let's look to the left top corner. So here we are going to find the mass number. And by definition, this is the number of protons plus the number of neutrons. So therefore, for this particular element, we have mass number equals to 20. Therefore, the number of neutrons is going to be equals to 10. Okay. And finally, number of electrons. Look now at the top right corner. If there is nothing there, it means the charge is 0. Therefore, number of electrons is the same as the number of protons. All right, so this should be clear for everybody at this point. If not, let me know. And so let's tackle here the final example. So now the biggest difference here is charge. So I'm going to move a little faster here. So Cl stands for chlorine. Number of protons is the atomic number, or the number on the bottom left corner. So it's still 17, okay? So we are still talking about chlorine. Mass number, that's going to be right here on the top, 36. And that's going to give us still 19 neutrons. And now here, the biggest change is the charge, all right? So we have a -1 charge. That means we have 1 electron in excess. Therefore, number of electrons is going to be 18. Okay. Never ever change the number of protons. You will always play with the number of electrons to match the net charge of the element. And if you want to double check if your number of electrons or net charge is correct, you simply subtract the number of protons to actually subtract the number of electrons to the number of protons, okay? So if you are not sure, just do this simple math. Okay, so I don't want to jump the horses here to talk about where this electron is going from or coming to, so we will keep this simple for now. Okay, any questions until this point here? So if everything is good, let's move on. Okay, let me go back here to the PowerPoint. Okay, so we are going to do some practice regarding this kind of exercise. Okay, so let's talk a little bit more about the periodic table. So the periodic table contains all the elements that we have found so far in nature. The number of the element, or the number here on the top left corner, is always going to be the atomic number of an element. And remember that the atomic number is unique for each element. So that is the first thing you are going to extract from the periodic table. So sometimes you will see the atomic number on the top left corner or just on the top here. And second thing that we will find in a periodic table is a number at the bottom, and this number is the average atomic mass. So be very careful here. I just showed you the mass number, which is completely different from the average atomic mass that you see here in the periodic table. Mass number is defined as the number of protons plus the number of neutrons. It's always an integer, while average atomic mass is a different concept that I will show to you soon. Okay, very good. Let's talk about isotopes. Okay, some elements share common number of protons, but different number of neutrons. Therefore, isotopes are elements with the same number of protons. So let's look here at neon. So neon will show up in nature as three different isotopes. See here, all of them have 10 protons. However, they have different number of neutrons. All right, so pay attention here. Just the fact that these three elements have 10 protons, that means all of them are neon. However, the first one has 10 neutrons, second one 11, and third one 12. Therefore, they will have a different mass number. Here I'm calling it atomic mass, which is the same thing. So for the first one, we have mass number 20. Okay, so just adding neutrons to protons. Second one is 21, and third one is 22. There is a particular way to name isotopes from an element, and the nomenclature is very simple. We are going to use the name of the element dash the atomic mass or the mass number. So for the first one, we are going to name it neon dash 20. Second one, neon dash 21. And third one, neon dash 22. Okay, so just be sure that you have clearly the concept of isotopes. Okay, elements that share common number of protons but different number of neutrons. To name the different isotopes, we are going to use name of the element dash mass number or atomic mass. Alrighty. Switch here. Okay, very good. So now it is a good time to introduce the concept of average atomic mass. In the case of the average atomic mass, we are going to take into account the contribution of each element to the total mass. For neon, we have 3 isotopes that can be found in nature, and we have the percentage of isotope of each isotope that we will find. So when we have a sample of neon, 90.48% is going to be neon 20, 0.27 neon 21, and 9.25 is going to be composed of neon 22. The average atomic mass will take into account an average of each mass that's contributing to the total mass of the element. Let me go back here. So to determine the average atomic mass, we are going to do the percentage. Percentage times mass for the isotope number 1 plus percentage times the mass for the isotope number 2 plus percentage times the mass for the isotope number 3. If you had more isotopes, you keep adding up, and this whole thing is going to be divided by 100. Therefore, the average atomic mass for neon. So let's look here. Isotope number 1, the percentage is 90.48. The mass of this isotope is 19.92. We are going to add the percentage of the second isotope times its mass, 20.99. And finally, the third one, 9.25 times 21.99. And all of that is going to be divided by 100. All right, if you got all the way to this point, just be careful with the math. Okay, so it's going to be a shame if you make a mistake here in the calculation. So according to my numbers, this is going to be 20.11. And the unit that we are going to use is atomic mass units, AMU. Put your result here in the box, and then I can clearly see where it is.
What does the percentage represent?
The percentage of each isotope.
Yeah.
So it means that if you have 100 atoms of neon, 90 atoms are going to be this isotope here, for example.
Okay, that makes sense.
So it's the amount of isotope that you find in nature. So that's why you have to take into account all the isotopes when you're calculating the average atomic mass.
Okay, thank you.
You're welcome. Thanks for the question. Okay, guys. So pay attention here. The sum of all the isotopes that you find in nature, of course, it has to be always equals to 100%, right? So if 1% is missing here, you can figure out using this concept. Okay. Any other questions? All right. If you guys don't have questions, I will keep moving. All right, let's go back to the PowerPoint. Okay, very good. So now we know the concept of average atomic mass, and attention again, average atomic mass and mass number are two completely different things. Okay, be careful on that. And to finish things up here, let's talk about isotones and isoelectronic elements. Some elements share common number of neutrons or electrons with others. Isotones, same number of neutrons. Okay? So you may have two different elements that share a common number of neutrons, and therefore those two elements are called isotones. For example, here we have carbon 13, 13 minus 6, that's 7 neutrons, and nitrogen 14, 14 minus 7, 7 neutrons as well. So therefore, those two elements are isotones. And finally, isoelectronic, two elements that share the same number of electrons. For example, sulfur 2 minus. If we have here a 2 minus charge, that means we have an excess of 2 electrons. Atomic number is 16. Excess of 2 electrons will give us 18 electrons. And argon 0, atomic number 18, neutral charge, that means 18 electrons. Same number of electrons, therefore sulfur 2 minus and argon are isoelectronic. All right, so let me tell you one thing here again. If you sit for 50 minutes, 3 days a week in my lecture, that's not enough. Okay, so in the lecture, I'm just covering the basics here. You have to go back to the book always, and you have to do the homework before the deadline, okay? So that will push you to go back and read the book. If you leave for the last minute, guess what? You will not have time to complete things. Okay? Again, only watching the lecture is never enough. Okay, so on Friday, we will have the in-class assignment. I will post the assignment on Canvas. We'll have 10 questions. Again, if you did discussion and homework, you will not have any problems with the assignment, and I will cover everything all the way to today. You don't need to log in on Zoom. It's not needed. I will be online if you have any questions. So if you want to pop up and ask any questions, I will be here, and I may or may not answer your question, depending what your question is. All right, so Monday, we will not have lecture, and we will resume back on Wednesday. Okay, so starting next week, if you are around and you want to come to the lecture hall, I will be there lecturing. If you want to not come, so the lecture will be on Zoom as well. All right. Okay, so with that being said, I think that's a good point for us to stop. And I will see you Friday or next week. Okay, bye-bye.
All right, thanks, Professor.
Thank you.
Thank you.
Thank